All right, hello class. All right, so we're going to talk about kinematics in one dimension. Now, kinematics is a study of motion. So we want to be able to just describe the motion of an object. And right now we're restricting ourselves to one-dimensional motion. So, you can just draw a line. Say an object can move along this line, it can move forwards or backwards, but can't leave that line. And then later we'll generalize to two or more dimensions, but really stick with two. Okay, so what we mean by describing motion, we want to be able to say like we have an object. We want to be able to say like where it is and how it's moving. And in particular, when we talk about how it's moving, we could say like how fast is it going, but it's possible that it's not moving at a constant speed, so its velocity can be changing as well. And when we have a change in velocity, we call that an acceleration. So we have to first define three things: position, velocity, and acceleration. So for position, we just use the variable x. So, kind of fundamental to this, we first have to have a coordinate system in mind. So I drew a coordinate system, x equals 0, and just to be clear, let's say right is the positive direction. Now, it does not have to be that way. We can draw any coordinate system we want, and often we will draw different ones than this, just horizontal line. An example of one-dimensional motion, let's say you place like a marble on top of an inclined plane, and it's going to move in this direction. So if we were doing this problem, it might make sense to just say, like, this is our coordinate system, and say x equals 0, where this object is going to start. And if we drew the slope the other way, it would be moving in this direction. And because it's moving in that direction, we could call that our positive direction, even though it's kind of pointing to the left. So we have a lot of freedom when it comes to defining coordinate systems. But once we have this coordinate system in mind, if I tell you this object is at x equals 2 meters, well, 2 is a positive number, so you go 2 meters to the right of the origin, and you know where the object is. Now, let's say that it is at a position, let's call this x1, and say that it's at that position at a time t1. Now, later on, it might not be at that same place. So later on, we could say it's at position x2 at time t2. And so overall, the object moved from x1 to x2, and we're going to find something else called displacement. So displacement, we use the symbol delta x. Delta is a symbol we frequently use for change. It's that Greek letter, basically just a triangle. It just means change. So the change in x. And we define it as x2 minus x1. Typically, delta means like the final value minus the initial value. There are some exceptions to that, but that's usually the case. Okay. So, displacement could be positive or negative. Like if x1 is bigger than x2, then the displacement is negative. That would mean the object was moving to the left. So if we have a positive displacement, if we're going from x1 and x2, that's a positive displacement that's moving to the right. Okay, and then we're going to define velocity. Now, this one is actually a little bit difficult to define. So, what do we mean by velocity? Now, right now, I'm calling it velocity, sometimes, speed. Those two are mostly interchangeable, but there is a distinction between them. But for now, we can just kind of use them interchangeably. So what do we mean by velocity or speed? That means that an object is moving, and the more quickly it's moving, the greater its speed. And so in order to say something is moving, it has to actually move. It has to start somewhere and end somewhere else, and it has to take some time to get there. And so we're going to define the average velocity as displacement over time. So, like in this case, let me write this out. Now, like in this example, we start at x1 at t1, end up at x2 at time t2. So that's how we would define the average velocity over that time interval, delta t. And again, velocity can be positive or negative. Here, if we start at x1 and end at x2, that'd be a positive velocity because we're moving in our positive direction. Okay, now this is it's an average velocity. It doesn't tell us too much information, really. Because all I've really told you is that we're starting here and ending here, and how long it takes to get from one point to the other. But we have no idea what happened in between times t1 and t2. Now, maybe this object we're describing, maybe it starts at x1 at t2, and it just sits there for a while not moving, and then it eventually moves and ends up at x2. Or maybe it started out moving rapidly in the positive direction, it just kept going for a while and then turned around and came back and ended up at x2. And so a lot of different things, or maybe it moved to the left and then turned around. There's a lot of different motions that could start here and then here. And we have no idea what actually happened if all we know is these two data points. And so what we'd really like to know, we want to describe motion, we want to know more details. We want to know everything that is going on. And if you think about, say your car, you're driving your car, and you look at the speedometer and it says you're going 30 miles an hour. Well, it doesn't mean that, 1 hour from now you're going to be 30 miles away from where you started. Because you might not be driving for an hour. You're probably not going to be driving for an hour, at least without speeding up or slowing down or changing direction. So what does that mean, that 30 miles an hour it's telling you? That means that if you're going to be traveling without changing direction or speeding up or slowing down, you'll travel a distance of 30 miles in 1 hour. But, obviously you probably won't be doing that. But, how does your car actually what is your car actually measuring? It's something that we call the instantaneous velocity. How fast, we have this idea, how fast is a car moving right now? And again, that's actually a fairly difficult concept to talk about because motion involves a change over some time interval. So what does it even mean to say right now? And so this was actually a very serious problem that scientists dealt with. It was not solved until really Isaac Newton. The idea of being able to define an instantaneous velocity. And Isaac Newton invented calculus. So I'm going to write down the definition of instantaneous velocity. So we have here, this is LIM, this stands for limit, which is something you study in calculus, which is not a prerequisite for this course. And that's a bit of a problem for us. But fortunately, what we're going to do is we're going to restrict ourselves to the case of constant acceleration. Now, acceleration is a change in velocity. So we will consider accelerations, of course, but say the acceleration is constant. In that special case, we can actually solve our kinematics, this problem of kinematics in one dimension. We can solve that algebraically. But for general motion, to describe the motion of a particle in general, very often that does require calculus. But in the constant acceleration case, we can do that. And fortunately, that's a very important case that comes up in a lot of real problems. Now, there are some problems we're going to consider where the acceleration is not constant, but we're going to have to do it in a different way. Okay. So what do we do with this definition? Formally, nothing. We can't use it, but the idea is if we take delta t to be a small time interval, like say you're driving your car, so you start at rest and then you hit the gas and you start moving, you speed up, and then you move at a constant speed for a while. Then maybe there's a stoplight, so you stop, and so your speed changes and it's constant for a while. Then it decreases back to 0. If you look at the average velocity over that entire time interval, it's not going to tell you too much. Well, it'll tell you kind of like your average speed over that. That could be useful information, but it won't give you any details about what's happening in between. And so what we like is, if you imagine a small time interval, not much is going to change if we make that delta t very small. How small, it depends on what you're doing. If you're driving a car, assuming you don't crash into something, your velocity is not going to change very rapidly. And so, a time interval of, a fraction of a second is good enough. But what this limit means is we have to consider different time intervals. Like, say you pick a large delta t, and you look at, you calculate your average velocity over that large time interval. And then let's say you shrink delta t. And you notice the velocity you calculate changes, and as you shrink it more and more, this average velocity keeps changing, but it changes less and less. And as you make delta t very small, you kind of get to this value that doesn't change anymore. So we can't go through and do the math, but just intuitively, that is the idea behind this limiting process. And if you take a calculus class, you get to this pretty quickly. And, but we can't do that. So that's velocity. Again, it's actually a fairly difficult process, or fairly difficult thing to talk about because we're limited mathematically. But let's move on to the last topic here. The last thing we're going to define which is acceleration. And acceleration is a change in velocity. So I'm going to define it so the average acceleration over some time interval is defined as a change in velocity over time, and the instantaneous acceleration same thing, except we take the limit that time interval goes to 0. Okay, so what we've done so far is we've defined position, which is just where an object is, displacement, which describes its net motion over some time interval, velocity, and acceleration. Now, usually what we want are these instantaneous values. And so now I can state our goal, the main goal for this chapter, this topic of one-dimensional kinematics. But first, I have to kind of ask a question, which, obviously I'm not expecting an answer because this is pre-recorded. But in an actual classroom, I always ask this question. Let's say you have velocity. Let's say it's a constant velocity. Say 12 meters per second. So we have some object, and you know it's moving at a rate of 12 meters per second. Now the question is, do you know where this object is going to be, say, 1 second later? And again, when I ask this question in class, students very often say, yeah, it's going to be 12 meters away. But you don't really have enough information to know where this object is going to be at some later time unless you know where the object started. So if we want to describe the motion of an object, we need to know where it started. If we want to know where it's going to be later. Kind of an obvious thing, but yeah. So that's one thing we need to know. And we also need to know how fast it was moving initially. Like we're going to say, we're going to look at the motion starting from now and describe it in the future. So we need to know, is the object moving in the beginning? Because if we don't know how fast it's going initially, we don't know how fast it's going to be moving later. And so now I can state our goal for this topic. So let's say we are given the following. Now this is pronounced x naught and v naught. That's the initial position and the initial velocity of the object. You can think of that as the position at t equals 0 and the velocity at t equals 0. So initial position and velocity, and we're also given the acceleration and the fact that the acceleration is constant. And our goal is to find the position and velocity as functions of time. And really this is kind of a complete solution to what we're trying to do here. Because let's say we have the position as a function of time. I can ask you, where's this object going to be in 12 seconds? And you can just plug it in here. Plug in t equals 12 seconds, and you know where the object is. You could also plug it in here and find out how fast it's moving. And so, yeah, if we can do this, if we can find the position and velocity as functions of time, we know everything about the motion of this object. Now, obviously, these equations are only going to apply as long as the acceleration remains constant, which can't be forever. There has to be, we have to have a limited time domain where these are valid. Because if something keeps accelerating, it's going to get moving. It's moving fast. It's eventually going to hit something. So, yeah, it's hard to have just continuous accelerated motion. Something's going to happen eventually. But this is our goal. So now we want to go about solving this. Now, I guess I'll leave that up for now. Again, keyword here is constant. If you don't know if the acceleration is constant, these equations we're going to come up with, you simply cannot use them. So we're going to start out, I have to point out one fact. In the case that we have a constant acceleration, let's just say a concrete example. If we look at the units for acceleration, we have velocity on top, that would be meters per second. And then over time, which is in seconds. And in the old days, they used to pronounce this meters per second per second. But now what we do is let's multiply the top and bottom by a second. So those cancel out. And we get meters per second squared. Either one's fine, but that's usually what it's called now. Okay, so let's say the acceleration is 2 meters per second squared. What is the average acceleration? Well, it's 2 meters per second squared. And so basically, in this case with constant acceleration, the average acceleration is just the acceleration. We don't have to worry about this limit. And so we're going to start by looking at the velocity equation first. Or we can say that A is equal to delta V over delta T. And again, this is completely valid that we ignored this limit, but that's only the case if we have a constant acceleration. Okay, and so now let's multiply both sides by delta V, or sorry, by delta T, and then I kind of flip the side, so delta V is on the left. And let's consider, it's a change. So let's just say, in general, we can say V2 minus V1 is equal to A times T2 minus T1. Where these are any 2 points. Like V1 is the velocity at time T1, V2 is velocity at time T2. But what we're going to do is, let's say that T1 equals 0, and T2 is just equal to T. So what we're doing is we're calling this first point, let's just set the clock at T equals 0. And then T2 is some arbitrary point where we want the velocity as a function of time. We want to be able to plug in anything for T. So we're not really looking at 2 particular points. Let's just leave T2 to be whatever future time you happen to be looking at. And then V1 is what we call, it's at T equals 0, so we call that V naught. And V2 is then just V. That's a velocity at time T. And so now if we plug this in, what we have is V minus V naught is equal to A times T. Because we have, T2 minus T1 is T minus 0, or T. And now what we do is let's move this V naught term to the other side. Okay. So here we are. V equals V naught plus AT. So yeah, we move this term to the other side, and now we're done. We have the velocity as a function of time. Because remember, we were given the initial velocity and the acceleration. So let's look at a concrete example just to see, make very clear what we've done here. Let's say we have an object that's moving at 9 meters per second. And say its acceleration is minus 1 meter per second squared. Now that negative means that it's accelerating to the left. Like say right is our positive direction. Like right now it's moving in the positive direction. So this minus sign means that it's slowing down. That's called a deceleration. It's often called that, but that's one of those terms we can do without just calling it an acceleration either way. And let's say we want to know how fast this object's going to be going after 4 seconds. Again, you can put anything you want in for t. Let's just look at one particular time later. So we'd have v is equal to 9 meters per second. And then we have plus a, but a is negative, so let's say minus 1 meter per second squared times 4 seconds. Now, very important to pay attention to units. Here we have a second over a second squared, so one of those is going to cancel. And so we have meters per second and meters per second. You can never add terms if the units don't match. So if these had different units, something is wrong. And so then, just doing the subtraction, we see that after 4 seconds, this object is moving 5 meters per second. So it's still moving in the same direction, but it's moving slower. And again, you can plug in t2 equals, you can plug in t equals anything you want, and you know its velocity. So basically, we know the velocity of this object at all times with that little, constraint that this is only valid while the acceleration is constant. Eventually it'll hit something or something's going to change. Okay. So we did half of it. But unfortunately we did the easy half. Because now we want to find the position as a function of time. And it's kind of the same thing we did before, except here we cannot ignore this limit. Sure, we were able to ignore the limit here because the acceleration was constant. But here the velocity is not constant because we're considering accelerated motion. So we can't just get rid of this, this limit. But what we can do, let's look at V average is delta x over delta t. And so we can say that delta x is equal to V average times delta t. So that's totally valid. But now we need to know what this average velocity is over this time interval delta t. And in general, that is a very difficult question to answer when you have like the average value of a function. So real briefly, let's just look at like why this is a problem. Say we have some random function. So let's say it starts at A, ends at B, and we want to know the average value of this function over this interval A to B. It's probably somewhere in here. But to calculate it precisely, like average value of, if you just have a set of numbers, it's very easy to calculate in theory. You just add up all the numbers and then divide by the number of numbers that you had. Problem is, we're talking about a function, over like this real number line. And so this function has an infinite number of values. In the real number line, there's an infinite number of points between any 2 points. And you can't add up an infinite number of points and then divide by infinity. That's a bit of an issue. And the solution to this, of course, like usual, is calculus. But because we're dealing with this case of a constant acceleration, and again, I'm just going to state this for now. We're going to show that we'll talk more in detail later. If we look at the velocity as a function of time, if you have a constant acceleration, let's say you start out with some initial velocity, and you have a constant acceleration, we're going to have a straight line. It's going to be a straight line connecting, this is at t equals 0, this is at some later time t. So we just have a perfectly straight line, assuming that the acceleration is constant. And in this case, the average velocity, I'm going to have to write this somewhere. We just cram it in the bottom. So it'd be, it should maybe intuitively make sense that it's right in the middle. If you look on this vertical scale, V naught and V, it's right in the middle. So that'd be V naught plus V divided by 2. That would be the average velocity over that time interval. Okay. So let's plug that in. So we have delta x would be V naught plus V divided by 2 times delta t. Okay, so we're going to do a couple of things now. Remember this V, this was the velocity at the end of this time interval, which is V naught plus AT. So we can plug that in. Again, that whole thing is over 2 times delta t. And let's do something similar to what we did last time. Let's consider 2 points. Let's say t1 is 0, and t2 is at arbitrary time t, and then x1 is x naught, and x2 is just some arbitrary position x. And so if we plug that in, delta x, that's x2 minus x1. I don't know if I can fit it here. I'll just write it below. X minus x naught, that's delta x. Here, let's add this up. We have 2v naught plus at, that whole thing over 2. And then delta t, that's t2 minus t1, that's just t. So, okay. Now, we're almost done. Now, I should point out that what we're doing is we're deriving these equations. Like this whole chapter is about kinematics, constant acceleration, one dimension. Basically, every question is going to involve what we're doing here. But don't be intimidated if this algebra is a bit much, because deriving the equations, we're going to get this equation, but once we have them, then we can use them. So like all this stuff we're doing, we're not going to have to do this every problem we come across. We're just deriving the basic equations, and then we can use them in the future. But let's finish deriving this. So we can break this fraction up into two pieces. We have a plus. So we can say it's 2v naught over 2, which is v naught. And then we have at over 2, which is 1/2 at. Again, that was our fraction. We just rewrote it. And that whole fraction was multiplied by t, so parentheses were needed there. And now for the final step, what I'm going to do is add x naught to both sides. So again, if we add x naught, that cancels it here. Now it's on the other side. We add x naught to the right side, so it's there. And let's distribute that. We have v naught t. And then plus 1/2 a. And then, at times t. That'd be 1/2 at squared. So we have x equals x naught plus v naught t plus 1/2 at squared. And basically we're done. So if we have this case, constant acceleration, where we know the initial position and velocity, we know the position and velocity of this object at all later times, as long as that acceleration remains constant. So in a sense, we can say we're done with chapter 2, let's move on. But of course, we need to practice this. And there's one kind of class of problems that occurs reasonably often that it's kind of hard to work with these equations. Like an example, we'll actually do this example. So there's one in the notes. Like say a plane lands on a runway, and so the runway is like a certain distance, certain length, and so the plane touches down, and it has to slow down to almost 0 by the end of the runway. And so we don't know how long it's going to take to get to the end of the runway. But, these two equations are all we need to solve the problem, but it's fairly difficult because we don't know time. Time doesn't really enter directly into this problem. And so for problems like that, we're going to actually derive a third equation, which is not necessary. It's just a huge time saver when those problems come up. But I think I want to do maybe one example. Actually, I'm going to try to get in the habit of doing sample problems in separate videos because, maybe later you want to just watch that part so it's easier to find. So I think this is a good place to stop because we just, derive these equations. So what I'm going to do is I'm going to talk about that kind of third equation we can add to this and then do a few problems. But I'll stop here for now.